Hello, my name is Stanford Gibson. I am the Sediment Transport Specialist on the RAS team, and this is an excerpt from a class we just taught. I taught a class with Dr. Jay Pack on the new post-wildfire features in HMS and RAS. So before this, Dr. Pack talked about the new post-wildfire delivery methods in HMS, and after this, I talked about several applications we've done with the post-wildfire stuff in RAS. But I took this excerpt to include in our technical reference manual because it's kind of the most complete treatment I've given to the methods and the equations. So the idea here is that we're going to talk in some detail about the methods and equations that were used in the non-Newtonian algorithms in DebrisLib, which is what we use in RAS. This work was funded by the Flood and Coastal R&D Research Program of the Corps of Engineers, and this video was funded by the Regional Sediment Management Program, RSM. Once you actually have concentrations, then you look at those concentrations and you say, oh, wow, these concentrations are high. These concentrations are like, I don't know, 10, 20, 30, 70% by volume. Once you get into that range, actually, anytime you get over 5 or 10% concentration by volume, the water is no longer water. Basic equations that you and I have always used to model water, or even water with sediment transport, even water with a lot of sediment transport, they break down. The physics doesn't work. It is a different kind of fluid. And we all learned about this, in one lecture in Mechanics of Materials back somewhere between 5 and 50 years ago, depending on how long we've been out of undergrad. But now it's coming back to haunt us because we actually have a fluid that's what we call non-Newtonian. So this is what I'm going to do. I'm going to talk to you about the capabilities we have in RAS, and we're going to have to talk about the equations. One of the things you'll find about non-Newtonian and RAS, it's like non-Newtonian in HMS. It's actually pretty easy. You can get a Newtonian model running non-Newtonian, and once you know how to do it, in about 15 minutes. So I actually don't want you to do that unless you understand what's going on. And so we're going to talk about the equations. There's no way around that. Watch me do it. Okay, so that's where we're going. Okay, so let's talk about what's in RAS. This is in Montecito, and every time I go to a debris flow site, I almost don't believe it. The size of material that's being transported, this boulder here is larger than the channel itself, right? Obviously it was transported in the floodplain, but it almost seems like science fiction. And it almost is because it's non-Newtonian, and all of our intuitions have been calibrated to Newtonian flows. And so I need to say here that I am presenting on behalf of my colleague, Alex Sanchez. Alex is the other sediment specialist at HEC, except he wears a lot of other hats. He's actually the RAS kind of numerical methods specialist. He's the 2D sediment guy. And so he coded all the 2D sediment stuff and all the 2D debris stuff. The debris stuff is in 1D and 2D, but I'm just going to recommend that you use 2D always because if you start looking at these debris flow models, it's a very rare case that it's 1D, and 2D is going to be a lot more stable. Okay, so just to kind of get us in context, just in case anyone's kind of new to the HEC suite, the HEC develops lots of software. It's not just RAS and HMS, but most people use RAS and HMS outside of the core. So the idea is that HMS models the watershed and then feeds boundary conditions to RAS. And that's kind of the main thing we do. But then downstream not physically, but downstream in analysis, we have our economic tools, FIA and FDA, and our ecosystem tool, EFM, the ecosystem function model. And then we have these kind of enterprise software, HC-WAT, CWMS, RFT, that can run them all together or stochastically, and making them interact with like 1,000 realizations or 10,000 or 1 million realizations if you want to run it on the cloud. That's the basic context. But in this talk, basically, Jay went first because Jay goes first. We run HMS to figure out how much water and how much sediment, and then we send it to RAS. And this is really the way that we do it in the field as well. A lot of times the main question someone wants to ask is how big do I have to build my debris basin, or how much is my debris basin going to help? And so you run HMS, you get your debris load, you run the reservoir model that Jay showed you at the end. That's not just kind of a new cool feature in HMS. It's kind of fundamental to a lot of these analysis because you want to fill the debris basin. You want to know what the concentration is after the debris basin is filled. And so you do that, and then you send the excess downstream and you have a concentration or eventually a time series of concentrations to send downstream. Okay, so what's a debris flow? Someone's already asked this question. I was so confused by this early in the literature. People use the term debris flow to mean any number of things. It could mean that there's just a lot of trees in the water. If you go and type debris flow into YouTube, you'll just see like a wash in Las Vegas. The problem is that these terms have semantic range. When someone says debris flow, not everyone is hearing the same thing. And so we follow this taxonomy in RAS just because you have to choose a taxonomy, not because it's exactly right. Basically, the idea is that as you add solids to water, the fluid properties change because the physics changes. And so kind of most of my career, I've worked in sediment transport or clear water flow. And in clear water flow or sediment transport, the solids are rare enough that their interactions don't matter. Even in like very high concentration flow, alluvial flows like dam removals or sediment flushes, the sediment concentration is still on the order of like 3 to 6%. And the particle interactions when you're at 3 to 6% really don't matter. But when you start getting up into some of these post-wildfire events or these dam failure events, now you're starting to get into concentrations of 10, 20, 60, 80%. That your actual fluid is actually 80% solids by volume. Now the properties start to change. And so the idea is, at like 5 to 20 to 30%, we have what's called hyperconcentrated flows. Hyperconcentrated flows, the idea here is you're just adding viscosity to the water. These are all obviously heuristics and conceptual models, but go through this mechanistic progression. This is a mechanistic taxonomy, if you will. And so as you add sediment to the water or solids to the water is becoming a more viscous fluid. And so you have to kind of treat that viscosity differently. And so we call that hyperconcentrated flow. When essentially you can treat it like water, except it's got viscosity and a yield strength, which we'll get to in a little bit, then you're essentially in the hyperconcentrated flow world. But eventually, you get enough solids in the water that you actually get some kind of strange turbulent activity between the particles themselves. The particles create resistance to flow because the water has to move between them. And so now we're adding interparticle turbulence as something that happens within the fluid, and we tend to call that a mud flow. When you have enough sediment in there to cause interparticle turbulence, generally fine sediment, that tends to be a mud flow. A debris flow, by definition, in our taxonomy, not in every taxonomy, but in the taxonomy that we follow, a debris flow is where you have enough sediment in the system where the energy loss is what we call collision dominated. Basically, the particles ramming into each other is the primary way the fluid loses energy. That's what we call a debris flow or a grain flow in kind of the more technical term. But eventually, you get enough sediment that you're no longer in fluids class, right? You're in geotech class. And so at some point, you transition from a fluid to a mass wasting geotechnical event. And then you have to switch fields, right? And it's still wet. It's a very wet geotechnical mass, but it's like more of a plastic solid. And so now we're going to look at the failure plane. We're going to look at the geotechnical failure plane and the matrix strength. Essentially, you're no longer a fluid where the particle interactions are driving the energy loss. You're actually a solid with pore water pressure instigating the flow. All right, so the basic idea here is that you go from low concentration to high concentration. As you get higher concentration, you move from hyperconcentrated to mud flow to grain flow to debris flow or geotechnical. The problem is that this is not monoaxial. And so the issue is you can't just go in and say, okay, this is 15%, and this transition is 30%, and this transition is 50%, because it also kind of goes from finer to coarser. And so you can have a grain flow with a lower concentration of coarse material than a higher concentration of fine material. This is the Phillips and Davies taxonomy, which I think is pretty useful. And the idea is that it's one of these tripartite taxonomies where you have water, fine particles, and coarse particles. And basically, everything up here is the range of sediment transport that we're used to if you model sediment transport. Suspended load is over if you've got dominated by fine particles. Bed load if you're dominated by coarse particles. But eventually, you get into this zone, which we call mud flow, debris flow, or clastic flows. And the basic distinction is that when you're in a clear water flow or a hyperconcentrated flow, the sediment velocity is actually lower than the fluid velocity. That makes a lot of sense, right? In any sort of flow, as the water is moving, unless it's wash load or completely in suspension, the sediment is going to travel slower than the water. But when you get into these, what we call mud flows, debris flows, and clastic flows, now the solids are transporting at the same velocity as the water. Essentially, the solids are dominating the matrix enough that the water can't like seep through faster. It's all moving as one mass. And so that is what we would call a debris flow, which would be subdivided into mud flow, debris flow, or grain flow, and clastic flow, which is the geotechnical side of things, depending on whether it's fine or coarse. And then beyond that, you're kind of getting more into the geotechnical model. Now you're getting into like landslides. Now there are a number of these. Oh, and the other thing that I'll say is, as a sediment transport modeler, I do a lot of dam removals. I do a lot of reservoir flushes where the reservoir is full of sediment, and so you kind of open the hatches and it's essentially a temporary dam removal. And those all plot here, right? Those are all alluvial flows. They're not even hyperconcentrated. We are talking about really high concentration events. The idea here is that everything we've done so far in RAS, if you haven't done Non-Newtonian yet, basically the vast majority of your energy losses happen at one place. It's the transition between the water and the solid, which we call the cross section or the mesh. It's the boundary between the bed and the water. And so that's where most of our energy loss happens. There's some turbulent stuff, there's some other stuff, but basically that's where our losses happen. The idea here is that you're still going to lose energy at places where water and solids interact, but now water and solids are going to interact all through the water column. And so you're still going to have this boundary friction, but you're going to have interparticle friction, you're going to have energy loss due to collision, and you're going to have viscous energy losses within your fluid. And so you're just going to have to account for more losses. And so this is where we get mathy. Chester Watson at Colorado State, he was at Colorado State for a long time. He said this easiest way to lose an audience is to throw up the backward sixes, right? The partial differential equations. The backward sixes they're like gang signs of engineering. You try to signal that you're hardcore. These are the only partial differentials we'll look at. You should actually know these equations. This is what RAS solves. Right, these are the shallow water flow equations. We have two unknowns, flow and area, and so we have two equations, the conservation of mass and the conservation of momentum. And so in the conservation of momentum equation, the way that we figure out how much energy is transferred from the fluid to the solid is in these terms. These are the loss terms. We have the expansion contraction loss term and what we call the friction slope. The friction slope is just the slope of the energy grade line. And the energy grade line is the energy at each node. And so the slope of the energy grade line is just the spatial rate in which you're losing energy. So this is the 1D equation. The 2D equation gets more complicated, but it's the same basic idea. So I like to explain it with the 1D equation. Basically, the friction slope, you're just going to solve Manning's equation, right? Manning's equation has the friction slope in it. And so we're going to back out the friction slope from Manning's equation. The Manning's n doesn't show up in this equation. The Manning's n basically works through Manning's equation to give you the friction slope. That's all you're doing. You're just defining the losses of the energy losses in the momentum equation. And then you've got your expansion contraction losses. But what you'll notice is that these are additive. Right? I've taken my friction losses and I've just added my contraction expansion losses to them. Because we have them in terms of a friction slope, we can just add them. Well, that's the key to non-Newtonian flow with what we call the rheological model or the single phase flow model. We're just going to add another one. We're just going to add another loss slope, which I'm going to call the internal loss slope. And it's really just all of these terms. The the Manning's equation gives you this term, which gives you the friction slope. Now SI is just going to be a slope that basically computes the energy loss from all these internal processes. And so this is the viscous and internal loss term. And it's additive. We're just adding it to the other losses. This is not magic. You know, non-Newtonian looks like magic in the field. It's not magic in the equations. And so all we have to do is take these wild internal diverse processes and get them into one slope. Well, how are we going to do that? That does seem like a challenge. Well, it's a challenge that was taken on like 80 years ago. This is really well-established theory, and it comes out of the equation for shear stress. Shear stress is gamma RS, the unit weight of the fluid times the hydraulic radius, or you can just assume the depth for a wide channel, times the friction slope, which means that the friction slope is the bed shear stress over two parameters we definitely know, the unit weight of the fluid and the depth. Well, that's interesting. If we can take all of these processes and put them in the terms of a stress, then we can back out a friction slope. Well, how are we going to do that? So our internal loss slope is just going to be this kind of weird internal loss shear divided by the unit weight of water over depth. So how do we get this weird internal loss shear? Well, there's a whole field of inquiry which looks at what we call stress-strain relationships. It's called rheology. And rheology is just how different materials deform under stress. And so if we can propose a strain, then we can back out a stress from a rheological model. Okay, hopefully that's kind of the end of the partial differentials and the big words. Because a rheological model, it's just a relationship between stress and strain. And so the simplest rheological model is what we call the Newtonian model, right? And that's the gray line here. And the idea behind the Newtonian model is that when you apply a stress to water or anything Newtonian, it strains at a linear rate and immediately, which means it has an intercept of 0. That's the simplest model. That's a rheological model, but it's so intuitive to us, we don't give it a fancy name. Now things are going to get a little less intuitive, so now we talk about it as rheology, but it's the same thing. The second simplest rheological model is what we call the Bingham plastic, and that's this blue line here. And the idea behind the Bingham plastic is that it's still a linear stress-strain relationship. Actually, it's going to have a little bit of a higher slope because the slope of this line is actually going to be the viscosity of the fluid, and it's going to have higher viscosity. But then it also has the opportunity to have a non-zero intercept. If it has a non-zero intercept, what does that mean? Well, it means there's a certain range of stresses that don't produce any strain, which means if you just kind of tap your finger on water, it's going to move. But if you just kind of tap your finger on a debris flow, it's not going to move. You have to kind of push it, right? And so it has this non-zero intercept where a certain range of shears don't cause movement. Or that's actually more important in RAS on the other side. Because if water is moving, when does it stop? Well, if there's downhill, it's going to keep moving, right? It stops when it kind of hits the ocean or a puddle. But a non-Newtonian fluid, a debris flow, you'll go out and kind of look at a debris flow, and the debris flow will like run down a road and then just stop. Because a debris flow has internal strength. And if the internal strength is higher than the stress, it'll just come to rest. And so this is one of the things that we have to do with debris flows is they have to be able to come to rest or you'll really overpredict where they'll end up. And so the Newtonian plastic, basically you have this strain, which we'll get to, we can compute that in RAS, times the viscosity of the fluid. That's the nice thing about the Bingham plastic model is that the slope of this stress-strain relationship is just the viscosity of the fluid times some yield strength, the strength of the material has before it starts to move, the stress under which it can be static. And so if I'm telling you, if you just kind of stipulate with me that RAS can estimate the strain, then all you need is some estimate of the viscosity of the material and of the yield strength, which is harder, it is, and you can compute a shear stress, a stress-strain relationship. Well, now you have your magic stress. Now you can compute an internal loss slope, plug it additively into the momentum equation, and you're good. If you accept the assumption that your fluid deforms like a Bingham plastic. And so this is called single phase transport because we're assuming that the whole fluid is just is one type of thing. The people who are not fans of single phase transport say, well, it's actually two-phase transport and the phases interact a lot, and this is a pretty big assumption. It is an assumption, but you'll see in the next section, it works pretty well in most settings. But a fluid or a material doesn't necessarily have to have a linear stress-strain relationship, and often these debris flows don't. And so they can be nonlinear. In fact, they could be quadratic, which we call shear thickening. And so the idea behind a positive nonlinear or a convex nonlinear stress-strain relationship is that as the shear increases, the viscosity increases more. And so it becomes actually harder to strain the material as you apply stress. Or it can be shear thinning. And so it actually becomes easier to deform the material as you apply stress. And so these nonlinear models are other ways to model these flows, and we have these in RAS. They become more difficult though, because the Bingham model, you just have to estimate these two parameters. With a quadratic model, with a nonlinear model, you have similar parameters, but now you've got this term. And what is that? What is that physically in the world? Well, if someone hasn't done that physics for you, then it just becomes kind of a empirical coefficient. All right, so let's look at how the rheological models tend to play out in our taxonomy. Basically, if you are in hyperconcentrated flow, you're definitely in Bingham plastic world, generally where you're going to be. If you are in this turbulent or dispersive, according to O'Brien, who did a lot of this work, you're probably going to be in the quadratic world. You're probably going to have a dilatant or a shear thickening model. Now, I have not found that to be the case. In the modeling I've done, I've found that usually the Bingham plastic gets me where I want to go, and I tend to like simpler models when I'm dealing with uncertain processes because I don't like dark parameters. I don't like parameters that I don't understand. And so the simpler the model I can use so that I understand the sensitivity of my parameters, the better off I feel like I'm going to be in the long term calibrating. And in general, I've found Bingham plastic works through this whole range. But we have a paper that I'll show you at some point that shows you can, if you use a nonlinear model, sometimes you can get better performance. And then when you get into the matrix strength, into the geotechnical model, then we're actually going to use a geotechnical model. We're going to use a Coulomb model to actually look at the failure plane. Okay, so I asked you to stipulate with me that we could compute the strain. All right, so I told you all you're going to need to find this magic shear, which becomes your magic internal loss slope, is the yield strength, which is hard, the viscosity, which is easier, because we're going to provide the strain for you. Well, what's the strain? Well, if you think about water, right, water translates downstream, and the top translates faster than the bottom. In fact, there's actually zero translation at the bottom. And so basically what most investigators have assumed here is that because water deforms as a function of the velocity, because you have maximum deformation at the top and zero deformation at the bottom. And so this comes from Julian and O'Brien, that basically the strain of the water, or the deformation of the water, is 3 times the velocity over the depth. And so that's what we use. We use that in RAS 1D or 2D. Now we have a strain. Now we have all the terms we need to come up with your internal shear stress to compute your loss slope. All right, time for some RAS screens, because everyone loves RAS screens. How do you get to these magical parameters? Where are they in RAS? Well, they're hidden. You need to know that you want them. And so these are flow parameters. They're unsteady flow parameters. You can't do this in steady flow or quasi-unsteady flow because this is fundamentally unsteady. If you go to options and then all the way to the bottom of options in your unsteady flow editor, you'll see non-Newtonian parameters. Lava is actually going to show up right under that. Lava's going to get its own thing. But lava is also going to be a flow parameter. That's getting weird. I understand, but it's also really cool. And so if you choose non-Newtonian parameters, you get this editor. And this editor kind of gives you all you need for all the methods I'm going to show you as far as modeling non-Newtonian parameters. But because it's a flow level parameter and not like associated with your geometry, you can use it for 1D unsteady finite difference or 2D unsteady, which is finite volume. Now, if I have a choice, even though I tend to be more of a 1D sediment modeler, I'm going to try to do it in 2D. A, because most debris flows are 2D, but B, because 2D is just a lot more stable. Finite difference can't go dry, and so your debris flow can't come to rest. You can't have it come to rest and be dry at cross sections downstream. So in general, 1D unsteady is not getting you. You want to do this in 2D. We are looking at putting it in 1D finite volume. I don't know if you know this, but we took the finite volume solution in 2D. Because it's so much more stable, we brought it into 1D. And so you can run your 1D hydraulics in RAS with the finite volume solution that tends to be more stable. It's an option buried deep, but it's there. And so we're looking at tying that to debris because that would be a better 1D solution. And then we also can do 2D mobile bed, which I'll show you in a little bit. That's in a developmental version. I'm not sure when we'll release it, but it's there and it's cool. If you want to use a nonlinear model, we talked about how, in general, the Bingham model works pretty well. The Bingham model is just this first part, right? The yield strength plus viscosity times the shear. And basically, it's helpful to think about this as breaking it down into different additive components of the shear. And so you have a yield component of the shear, and you have a viscous component of the shear. And O'Brien did this work many years ago. He had this in Flow2D long before we ever did this in RAS. In his PhD work with Julian, he said there are these two other forces. There's this turbulent force, which he solved as a quadratic force. You can see the strain is squared plus some turbulent features, and a dispersive stress. This work comes from Bagnold. It's trying to quantify the collision losses, and it's a function of, again, the strain squared. And so if you want to use a quadratic equation but don't want to parameterize it, the cool thing about O'Brien's equation is it gives you a quadratic equation, but still only requires you to put in the yield strength and the viscosity. And so you can get a second order result without needing more parameterization. Now, you also have to just kind of trust that O'Brien's science works, and sometimes it does, and sometimes I've found that just going with Bingham's a little bit better. Well, O'Brien's main contribution was trying to tie that quadratic term into the physical reality and what's actually going on. So it's quite clever. But then, if you want to invoke the geotechnical model, we're going to use the same basic rheological approach. We're still going to use this yield strength and the viscosity times the strain. So what's different? Like I thought you said this was going to be a geotechnical model. That looks exactly like the Bingham model. Well, the idea is, what is the main thing that changes it into a geotechnical model? It's the statics, right? It's actually the yield strength. Once we basically lose most of our water, so basically you've got solids grinding against solids, and you've got a geotechnical failure plane, you're not really concerned too much about the velocity of that. It's slow. What you're concerned about is, when will it come to rest? And so basically, we're going to take the yield strength. We're not going to enter some sort of constant. We're going to make the yield strength a function of the geotechnics. And so we're either going to use the Coulomb equation or what we call the Volamy equation, which is a geotechnical model, but it has velocity in there because it recognizes that it's actually a dense fluid in flow. And so we'll quantify the yield strength as a function of the geotechnics. And so the idea is, you kind of, at some point, you move from this collision-dominated material to a friction-dominated material. Okay, so what I'm showing you now is a developmental version of RAS. We don't have this active yet, but this is where we want to go. How do you decide which of these equations to use? Well, you could look at the strain and the stress and the properties of the material and decide on the fly. We could just have you choose an equation, or RAS could choose an equation based on the changing properties of the material versus the velocity. And so that is something that we're working on. We don't trust it yet, but that is something we're trying out, and it will help you kind of think about which equation to use before RAS will choose it for you. And there are 3 dimensionless numbers. People in sediment transport, we love our dimensionless numbers. We're just like, if it can't be dimensionless, don't give me a number. And so we have the Bagnall number, the Savage number, that's like the coolest name number in the world, and the friction number. And basically, you have these terms that define 3 stresses: the viscous stress, the geotechnical stress, and the internal collision stress. Do those sound familiar? I hope so. We've been talking about them for a long time, right? And so basically, these different stresses are all in these dimensionless numbers, and we compare them. And they give us thresholds. Basically, if internal shear stress from grain collisions is a lot greater than the viscous stress, well, that is actually a quantitative threshold for moving into a grain transport or a debris flow model. And so the idea here is that you can actually make these transitions quantitatively, or if you have to defend these, we have this basic threshold of any concentration above 5 to 10% is a hyperconcentrated flow. You want to start using Bingham above 5 to 10%. But then you can't just use concentration because there's too many other things going on. And so the Bagnall number of greater than 450, and these numbers come right from Richard Iverson, the debris flow specialist of the last 20 years. And then the friction number, if it's greater than 100, you're in the Coulomb zone. And this is Iverson's plot where he actually plots the zone of debris flow on those numbers, which is, this is now getting much more defensible and quantitative. So then there's one more equation I have to tell you about, and that is the generalized Herschel-Buckley equation. The idea here is that, okay, let's say you want a nonlinear equation, but you don't really trust that this describes the world. This was a very clever approach by O'Brien, and sometimes it works, and sometimes it doesn't. And basically, you've got a quadratic model, but the coefficients are defined for you. What's always true about this quadratic model? Well, it's always positive, right? You never have like a negative exponent. It's always to the power of 2. And if you look at people who have actually measured these powers, the powers are often like 1.4 or 0.8. It's very rarely to the power of 2. And so the generalized Herschel-Buckley equation takes the Bingham equation and it says, instead of calling this viscosity and raising it to a power of 1, let's raise it to an arbitrary power. And then if you raise this to a power, this is no longer viscosity. And so, but we'll just make it a linear coefficient. It won't be viscosity, but it'll be a linear coefficient to the strain raised to this power, whatever it is. And so if you know these, if you have a sense of what these are, if you know that your material is dilatant and has a power less than 1, you can go parameterize this and you can be very precious about it. Lab studies like to do this. I've never used this in the field because how do I know? Like, how would I know if it's dilated? If this is the power of 1.5, well, this is no longer viscosity. And so I'm outside of anything physical. And so I've used this for lab studies who have measured these, but I haven't actually used them in the field. And then, of course, if n equals 1, well, then it just collapses to the Bingham equation, and the K becomes the viscosity. But what it does is it does allow you to do both kinds of nonlinearity. If n is greater than 1, you get this dilatant shear thickening. And if n is less than 1, you can get this pseudoplastic or the shear thinning. And I do think that if you're kind of using RAS for industrial purposes, which I suspect might happen now that we're non-Newtonian, and you actually kind of know the properties of like ketchup, or there's a famous disaster where there was look up a Boston Molasses disaster on YouTube. There was a giant vat of molasses in Boston. It's actually quite sad because it was devastating, but like it collapsed and the molasses ran through Boston, material with kind of a known property that you might be able to estimate. And so if you choose the generalized Herschel-Buckley, you're going to still use a yield strength, and you could actually use a geotechnical one if you wanted. But then you're going to go in and your Herschel-Buckley parameters are right. So a lot of these equations need a concentration. Partially why you need a concentration is you don't actually know the yield strength or the viscosity, and so we've embedded equations that will compute those for you based on the concentration. And so you get to put in one concentration. hopefully in 6.2, one of the things we're working on is we're going to give you a time series of concentrations. And so you can actually go in and say, you know, my concentration rises and falls. That's kind of cool, but it's still not really cool enough, because if you've got a long model, will the whole model have the same concentration rise and fall together? No, it changes with time. And we're doing a dam failure. We want like clear water at the beginning, and then we want the water to kind of get more concentration as time goes on. Well, we're working on two things to do that. One is we're working on a fixed bed advective diffusion model, where now your concentration time series isn't just for the whole material, it's for the inflowing boundary condition. And then we'll use a very simplified advection diffusion model, not, again, fixed bed or maybe just deposition, that will route your concentration downstream. That might not be till 6.4 or something like that. And then the other thing is we are building a mobile bed model. A mobile bed non-Newtonian model. So you turn on all the non-Newtonian parameters, and then you allow the mobile bed model, the sediment transport model, to scour the sediment and put it in concentration, and then you actually have a dynamic concentration. All of those are hard, and they're hard to develop, they're hard to apply, and we're working on them right now. The time series of concentration will be the first thing that shows up. But for now, you get one concentration. All right, back to the polls. If 1 liter of mixture, this is a mud. If 1 liter of mud includes half a liter of solid and half a liter of water, which would be larger? The concentration by mass, the mass concentration, the mass of the solids divided by the total mass, the volume concentration, which is the volume of the solids divided by the total volume, or these things are not different. They will be the same. And there is no shame in this question either, because it is so confusing. And so I'm going to take the next few slides to explain it, but just to make sure everyone's awake and to create appetite for the answer. Well, let's think this through before I give you the answer. There are lots of ways of defining concentration. And if you're confused by that, good. It means you've thought about it. Let me just give you 4. Concentration by mass, concentration by volume, parts per million, milligrams per liter. If you look at Julian's textbook, he has a very helpful chart in there that helps you convert between them. And what you'll notice is that at concentrations that we're used to dealing with, the parts per million and milligrams per liter are essentially the same. People will ask me, how do you convert parts per million to milligrams per liter? I'll say, you just did, right? Like, that's essentially the same. But as you get into hyperconcentrated flows, parts per million and milligrams per liter start to diverge because the concentration by mass and the concentration by weight are so different. So think about this with me. If you have half a liter of water and half a liter of sediment, well, liter is volume. So what's your volume concentration? It's 0.5. It's 50%, right? Your material is half solids by volume because it's half a liter. But what's heavier, the solids or the water? Well, the solids are heavier. So if you divide your mass of solids by your total, you're going to get a higher number. It's going to be closer to 0.7 because the specific gravity of your solids is about 2.6 times the specific gravity of your liquid. And so if you look at your concentration by volume versus your concentration by weight, the concentration by weight, if you choose 50%, which is 0.5 in our example, it's going to have a concentration by mass of 0.72 because we have these equations that compute, that kind of move us back and forth, but they're conceptual. You're going to have 50% of your material has a specific gravity of 2.65, and 50% of your material, and the balance of your material has a specific gravity of 1. So the concentration by weight, or the mass concentration, is going to be greater than the concentration by volume. Now, that matters because you have to put in concentration by volume, which means you have to compute concentration by volume. You might have it in milligrams per liter. You might have it in parts per million. You can't use any of those. You have to use concentration by volume. And It has to be in percent. The biggest mistake I see in non-Newtonian and RAS is people say, oh, I have a 60% concentration by volume, and they go and they type 0.6, and then they email me and they say, hey, your debris flow model sucks because I see no effect. And I say, well, that's because you have 0.6% concentration by volume, and I would mock them if I haven't done it myself like 3 times. So I get it, it's a problem. And I should throw an error message, and maybe I will on 6.2 if it's less than 1. But don't do that. Okay, so that's really confusing. What are we going to do about it? Well, we're going to give you a calculator because it's really confusing. And so what I've done is I created a concentration calculator. It's right next to the field. And so if you want to know what the concentration by volume is and you've got something else, or actually if you want to go any direction, you press the convert concentration, you choose the input units that you want. You can choose any of them. We even have another one here, water content, which is different. You define the specific gravity, usually going to be 6.25. In fact, I think I give you that by default. You put the input concentration, and we will convert it to all the others. And so if you have parts per million, you can put it in there, and we'll give you all the others. And so that'll help you. Eventually, you want to build an intuition for these different concentrations, but that'll help you kind of check your intuition. So how do you measure these parameters? I was making a big deal that, hey, all you need is yield strength and viscosity. Hey, you're home free. But then if we think about it for like 30 seconds, like, yeah, but how do I come up with those numbers? Those numbers, they're impossible. Well, you can come up with these numbers. There are machines that will help you measure this. You can't go measure it in the field because debris flows are incredibly dangerous and you don't want to get anywhere near one that's actually cooking. And so you could get one of these machines, and I think in the future we'll be doing more of this, but this is not what people do. There are 2 things that people do. And the first one is they use empirical equations. And so O'Brien has other equations, right? So O'Brien's name is all over this because he did a lot of the great early work. And he has equations for both yield strength and viscosity as a function of the volumetric concentration. Now you notice the volumetric concentration is in the power of those equations, which means it's very sensitive. But then there are other empirical coefficients. It's like, well, is it turtles all the way down, right? Like, are those empirical coefficients based on other empirical coefficients? Like, what are we doing here? Well, no, it's only one level of turtles. These empirical coefficients, Julian has a table, and so they're constrained. And one of the things that I found is that if I use the Bingham equation with the default parameters from Julian in the O'Brien equations. So basically, I'm not coming up with any of my own numbers. I'm just going and getting these numbers, and they're in the user documentation, plugging it into these equations, and letting RAS compute the yield strength and viscosity for me. That has worked most of the time. Most of the time, that's what I'm doing. I don't have better information. Now, I'd rather calibrate. But a lot of times if we're in an emergency management mode, we don't get to calibrate until afterwards. And then it turns out they performed pretty well. This is not ideal. I think the more of this post-wildfire stuff that we're doing, now that it's in RAS, and so lots of practitioners will get their hands on it, I hope that we will start to build databases of these numbers. And we'll start to develop more intuition. But for now, I said there are 2 ways to do it. 1, use O'Brien's equations with Julian's parameterization. Or 2, calibrate. Calibrate a lot, become familiar with the materials in your area. Okay, and where are these magical numbers? Well, they're where everything is, in the RAS users documentation. Now, we have done something different. We are moving away from a user's manual. Some of you may know that the RAS user's manual, the last time it was a manual, was more than 1,000 pages. And the millennials among us have been telling us for years that that's just dumb. That no one reads manuals anymore. And it's true. I mean, I'm an Xer and I don't read manuals. And so we are moving to what we call an online help experience. And what you'll notice is that I've developed a lot of videos. These videos are incorporated in the content of the old user's manual, but it's all just kind of morphing. Now we're actually putting the example data sets right in there. We're embedding the videos. We're embedding like help tips and things right in there. It's becoming better is all I can tell you. And so if you go to that, we have one just dedicated to mud and debris. Now these do have manuals on it. We're still in this user and tech ref paradigm. We're going to merge those eventually, but you can go in and we've got all the stuff a lot of the stuff that I showed you is in here. It's I think when it was a Word document, it was like 200 pages. So everything you need is in here. Eventually we'll hyperlink it all.